Okay, our first topic are looking at parent graphs of various functions that you will encounter in a typical calculus class. And so the first technique we're going to look at is making ordered pairs. So we're going to look at doing a table of values for a graph. And we're going to pick a couple of negatives and a couple of positives and just use the equation to find the other piece. So in the linear graph, when x is -2, y is -2. When x is -1, y is -1, 0, 1, and 2 accordingly. And then we're just going to go plot points over in the graph. And as we connect all of these points together, we get this nice pretty line. And then we're going to take a second and look at some properties of it. And this will become more interesting as we look at more complicated functions. For the linear parent graph, there's no restrictions on the domain. And so we can go from -infinity to infinity on the domain and on the range. Again, no restrictions there. And the y-intercept and the x-intercept, they both intersect at 0, 0 at the origin. And so there's that. And again, start with a table of values. And we're going to pick a couple of negatives and a couple of positives. And then as I square this, so -2 squared gives me 4, -1 squared gives me 1, 0 squared 0, 1 squared is 1, and 2 squared is 4. Sorry. Okay. And when I go plot points, and this time they start at the origin. Now, one thing about the quadratic parent function that's interesting, as you go out 1 unit in the left and right, you go over 1. So out 1, over 1. But when you go out 2, you go up 4. So over 2, 1, 2, 3, 4 right there. And then 1, 2, 3, 4. So it has this nice sort of out 1 over 1, out 2 over 4 pattern that we can sketch a graph with. So there's our typical quadratic parent. Domain and range. Okay, so now we actually got some differences in some of this. Domain, there's still no restrictions on x. So we still go from -infinity to infinity. And the range, however, the first y value that we actually encounter in the graph is at 0. And that is an included number. So we're going to bracket 0 up to infinity. And then the intercepts, both x and y intercepts, they both cross at the origin. So we're going to start with a nice table of values. And we're going to stick with our same numbers. They seem to be working pretty good for us. Although, we're going to be a little off the graph, but we'll see that in a second. Alright, and so if you cube it, so if you cube a negative, you actually get a negative. So this would be -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1, and then 2 cubed is 8. Okay. And then if I go plot those points, and we got the origin, -1, 1, let's see, -2, -8. So a little bit off of our, right there at the edge. So maybe not off. 1, 1, and 2, 8, all the way up there. And then connecting all of these points together, we get kind of this S-looking shape. And then as far as domain and range goes, alright, so going to domain and range, there's no restrictions on either one. So we're back to -infinity to infinity for both of those. And then they both cross at the origin, so the x-intercept is at the origin and the y-intercept is at the origin. Alright, next one is square root. Okay, so do the table of values. Now this one we get a little creativity with. And I say that because we got to think of some numbers that are easy to take square roots of. And normally I like to have 5 points, but given the size of this particular graph, I don't think we're going to get those in. So if I have 0, square root of 0 is 0, so we're good there. If I pick 1, square root of 1 is 1. And then if I go 2, well, square root of 2 is just square root of 2. That's kind of we could estimate that, but the idea is to pick a nice, easy number to take a square root of. So the next one up would be 4. So the square root of 4 is 2. And then again, when I think, well, what's the next perfect square after 4? That would be 9. And then the square root of 9 is 3. And you're probably thinking where the negatives go. Well, if we start taking square roots and negatives, we get I involved, and we don't want to graph imaginary numbers in our grid right now. There'll be plenty of time to deal with imaginaries later on, but not today. So we're going to go plot those points: 0, 0, 1, 0, over 4 up 2. Now I'm going to sort of estimate where 9 is on this, so you can kind of see that it's a slowly increasing graph. Okay. All right, now domain, we get some a little bit different numbers here. We start at 0, so we're going to include that. And there's no restriction on the positive side of the x-axis, so it's bracket 0 to infinity. And then the same thing for the range. And then as far as intercepts go, they both cross at the origin. So we don't worry about that. Okay. All right, so with absolute value, same, start with our table. This time we can put negatives in there. Now, what does absolute value do? Absolute value takes every number and changes it to a positive form. The definition of absolute value is actually the distance away from 0, so that's kind of why it does that. So how far is negative 2 away from 0? Well, it's 2 away. How far is negative 1? Well, it's 1. So it kind of looks a little bit like a quadratic, but not really. And then if I plot those points, it goes through the origin, and then sort of look like two lines that connect together. All right, and then domain, we don't have restrictions on it. We do on range, however. And then it crosses the origin again for the intercepts. So a lot of these parent graphs kind of have those similar type properties, but there are subtle differences between them.